Good afternoon, everyone. Welcome to week 11 of actually week 12 of the live sessions. This might be going to be our last live session. Maybe one more additional session I will be giving. Depends upon it's Monday time, same time. It's I think 15th of April. I will be giving one more live session. So I welcome you all once again to the live sessions on the finite element method presented by Danish Bashir from Structural Engineering Division, Department of Civil Engineering, IIT Madras. So in last class, we studied about the column buckling problem, and I showed all the formulation regarding the column buckling problem. Then we solved one numerical example on that also. So last class completed almost everything regarding the one-dimensional boundary value problems, and we saw a few examples in that one as well, wherein it was the application of the general one-dimensional boundary value problems. So in all those problems, we were seeing that we were using a two-noded element in which we were assuming that trial solution to be linear. Trial solution to be linear. So what we did is that for all the trial solutions to be linear, uh, so if we wanted to improve the accuracy of the solution, that is minimize the error, we needed a large number of elements or more number of elements to achieve the accuracy or to minimize the error between the actual solution and the approximated solution. But if we come continuously go on increasing the number of elements, we see that you people already saw that stiffness matrix goes on to become larger and larger, so that it eventually increases our computational cost. So in order to have an compromise, not a compromise, in order to remove this drawback of this lower order elements, where we have to use large number of elements with lower order. We can use higher order elements with very few number, and they can give us a very good accuracy. So in today's class, we will be seeing higher order elements for one-dimensional problems. Mm. There were advantages of the linear elements as well. The main advantage of the linear element was that it was very simple to formulate. And as I already mentioned, the drawback is that usually we require a large number of elements to get reasonably accurate solution. So today I will be presenting the finite elements for one-dimensional problems based on quadratic and higher order trial solutions. Okay. So if you remember, for two-noded element, we assume a trial solution to be linear. So in today's session, we will be seeing the higher order elements where the trial solution will be either quadratic or of some higher order. So today's topic is about higher order elements for one-dimensional problems. Elements for 1D problems. So actually what happens in is that when we use trial solutions of quadratic order or higher order, element formulation becomes a little bit more complicated. However, fewer of these elements are required for a given solution accuracy. Actually, they are especially useful if more accurate solutions, accurate solution derivatives are desired. Actually, we had lower order elements and we have higher order elements. Okay, so what we did is, what happens is that in lower order elements we assumed linear trial solution. First thing we assumed here, linear trial solution. Okay, trial solution for element. Okay, here what we can do is, here first point will be, we will assume quadratic or higher order elements, higher order trial solution, trial solution for element. Okay, this I am showing you the basic difference between the two things. Okay, the lower order element and the higher order element. Okay, then what else is that? Second thing is large number of elements, large number of elements required for good accuracy. Okay, accuracy. Actually, in this case, you need fewer fewer elements for good accuracy. What is actually another one here is that, actually here element formulation, element formulation is easy. Okay, here mm, element formulation is bit complicated. Okay, um, and what is the here? Why are higher order elements usually useful? Because they give, actually, for these give poor accuracy for derivatives, derivatives of solution. Okay, these give accurate derivative of solution. I hope you people got the point. What is the main difference between the lower order elements or the and the higher order elements? Because it's very important to know the difference between the two. Okay, so I want to mention here that, so we assumed solution to be equal to, we assumed u of x to be equal to, if you people remember it from the first class of third or fourth live session, we assumed it to be a naught plus a1 x. Okay, then what else was there? Here we will be assuming u of x to be a naught plus a1 x plus a2 x square, and so on, higher orders. Okay, this is a basic difference between the two things. Okay, this is your lower order elements, and This is your lower order elements, and this is your higher order elements. Okay. I hope the difference is clear to you guys. So now moving on to higher order elements, we have. So you already know that what are general steps in the formulation of finite element equations. We already know that. We choose the element shape, then choose the nodal degrees of freedom. That's important. And after that we obtain the shape functions, that is express the trial solutions in terms of nodal parameters, that is u1 and u2, and then substitute the trial solution into the equivalent function, and while using the variational method or Galerkin's criteria, and carry out the integrations. That is important. So now let's first see derivation of the shape functions starting from a polynomial, or we will see the shape functions. Shape functions, shape functions for second order problems. Okay, shape functions for second order problems. Actually, if you people remember while deriving the shape function for using for a two noded element with nodal parameters u1 and u2, where we got n1 and n2 as a function, where u of x was then n1 u1 plus n2 u2. We are doing the same formulation today as well, where we will start with a quadratic polynomial approximation, and the number of the coefficients in the polynomial is equal to the number of degrees of freedom of the element. It's important because if you remember in the two noded element, here there was two degrees of freedom. Here one node, 1 degree of freedom. This was second degree of freedom, second node. So we choose the polynomial u of x to be equal to a naught plus a1 of x. So there are two unknowns, okay, and there are 2 degrees of freedoms, okay. So if we have now three noded element like this, three noded element. So one DOF is here. So this is DOF. One more DOF and one more DOF. So total DOF degrees of freedom for this element is equal to 3. So the minimum U of x that we need to take in order to interpolate the solution within the element is a naught plus a1x plus a2x square. So it's important. For an element, for an element, the minimum order of trial solution is actually equal to the number of degrees of freedoms. Okay, number of degrees of freedom in element. Okay, so you remember this thumb rule. Okay, so this is our additional information that I give you. So now we are taking element. So now we are taking element like this. Sorry, which is having actually three nodes. Okay, so this is node 1, node 2, node 3. This is the element with total length of element is L. So polynomial approximation, and also the nodal degrees of freedom are u1, u2, u3. Okay, so minimum polynomial is the quadratic polynomial that I have to assume first. So a quadratic polynomial trial solution is required. polynomial trial solution is required. Okay, so it is actually which we assume u of x to be equal to a naught plus a1x plus a2x square. Okay, so this is here, it's important, and the value of the it is x1 here, x2 here, and x3 here. These are the points because this element is varying along x-axis. Okay, this is very important. So this is a typical quadratic element. Typical quadratic element. Okay, moving forward. So we know that actually if you people see that uh, u of x at x1 is equal to u1, u of x at x2 is equal to u2, and u of x at x3 is equal to u3. So we can equivalently write uh, u of x1 is actually equal to u1, and you have to put x1 in the trial solution, that is a naught plus a1 x1 plus a2 x square, exactly what we did in the lower order element few weeks ago. U of x2 is actually equal to u2, that is a naught plus a1 x2 plus a2 x2 square, it's x1 square here. So u of x3 is actually equivalent to u3, that is equal to a naught plus a1 x3 plus a2 x3 square. So if I name this equation as equation 1, okay, because we will need this later on. So so the solution, if I solve this, the solution of system system of equation 1, for if I solve it for a naught comma a1 and a2, I will easily get the value of a naught to be equal to, it is actually 1 by c. I will tell you what is the value of c later on. 1 by c, and it's a large expression. I will write for you people, x3 x2 square minus x3 square x2 times u1, okay, plus uh, x3 square x1 minus x1 square x3 times u2 plus x2 x1 square minus x1 x2 square u3, and you have to close the bracket, and then a1 is equal to 1 by c, it is actually equal to x2 square minus x3 square times u1 plus x3 square minus x1 square times u2 plus x1 square minus x2 square times u3. You have to close the bracket. And similarly, a2 is equal to 1 by c, and you will get the values x2 minus x3 times u1 plus x3 minus x1 times u2 plus x1 minus x2 times u3, and close the bracket. And the c that I have been continuously using is actually equal to the difference of the product, x2 minus x3, this value, x1 minus x2 times x1 minus x3. Actually, you will get these values once you will solve this system of equation for a naught, a1, and a2. You will get this one. So this is here, and actually this was equation A. So if I name this as equation A, okay, and I will name this as second, this is third, this is fourth. Okay, so what we will get using second, actually third up to equation fourth in equation A. Okay, so clearly we got the values of A naught, A1, A2. You have to just place these values here, A naught, A1, A2, to get the value of U of X. So when you will put all the values, we will finally get U of X to be equal to, actually we will get it in terms of U of X. We will get U of X in terms of something, some big term times U1 plus another big expression times U2, another big expression times U3. You will see what that is. So actually we will get it. So I will represent those expressions by N1, N2, N3. So if you will see the values of these N1, N2, N3 after simplifying the expressions, we will get U of X to be equal to N1 U1 plus N2 U2 plus N3 U3. Okay, where actually the value of this N1, N2, and N3, I will write it down. Okay, so N1 is, if we solve for N1, actually N1 is equal to 1 by C. So then you have to put this value, x3 minus x3 x2 square minus x3 square x2 minus times x2 square minus x3 square times x plus x2 minus x3 times x square. Okay, if you solve this and put the value of C, we will get x2 minus x3 times x3 x2 minus x2 plus x3 times x plus x square divided by C's value is x2 minus x3, x1 minus x2, and x1 minus x3. If you will see, there is cancellation of the cancellation of some terms, and n1 comes out to be finally x minus x2 times x minus x3 divided by x1 minus x2, x1 minus x3. Okay, this is the value of n1. See, if you see the value of n1, you will see there is some pattern following. So we can easily write n2. N2. Look, in the numerator, there is x minus x2, x minus x3. X1 is not there because it is for n1. And in the denominator, it is x1 and x1 minus x2 minus x3. Similarly, we can write like this. For n2, we can write easily. It has, sorry, it has x minus x1 because we don't have to write x2 in the numerator. X minus x1, x minus x3. And denominator is x2 minus other terms. x2 minus x1, x2 minus x3. And there is one more term, x2 minus x2. That is 0. We don't have to write that. I hope this is clear to you. Similarly, I can write the value of n3 for you people. N3 is equal to, we have to write x but not x3 above. X minus x1 times x minus x2. And in denominator, there is only x3 minus other two coordinates. x3 minus x1, x3 minus x2. So there is a nice pattern that it follows for higher order elements as well. So for higher order elements, we can easily write the shape functions. So you already know that n1, n2, n3 are known as shape functions. Okay, so far it was very easy. So if it was not an element with only three nodes, it was an element with five nodes. So how can we formulate the shape function for that one? So we have a very nice formula for that one, that is known as Lagrange interpolation formula for shape functions. So we will study now Lagrange Lagrange interpolation formula for shape functions. Okay, so uh, if we need to write an shape function for some element which is having n nodes, like there will be any element which will be having any n nodes. For example, let me draw an element. So for example, we are having some element, so it's having one node here. Sorry, it's having one node here, one node here. Let me draw it not perfectly. One, two, three, four, and there is some here like this, like this, and this is nth. This is first, this is second, this is third, this is fourth, this is fifth node, then so on. This is ith node, this is I plus one node, then following, this is n minus one node, this is n node. So this is n noded element. Okay. So for example, for ith element, not for ith node, we want to write the shape function. So the for ith node, the shape function will be, so this shape function is actually given by the polynomial that is known as Lagrange interpolation polynomial. Ni is actually equal to, so it's again equal to x minus x1, x minus x2, up to uh, x minus xi minus 1, but there should not be xi. Okay, x minus xi plus 1. You people can easily see that I skipped x minus xi here. So up to we will reach the last coordinate, that is x minus xn. So actually I forgot to write here. It will be here x1, x2, x3, x4, so on. It will be xi plus 1. This will be xn here. And corresponding nodal values will be u1, u2, u3, u4, u5, ui plus 1. Okay. Sorry, this is only ui. So this will be ui plus 1. This will be un. So actually, what are these? These are nodal values. Nodal values or degrees of freedoms. And these are coordinates or nodal points. Okay. These are nodal points. These are nodal values. These are the nodes 1, 2, 3, 4 up to this one. So this will be the numerator of this Lagrange interpolation for polynomial, and it will be having some denominator that is actually that ith node, xith minus x1. This is very easy. Xith minus x2 up to some xith minus xi minus 1. So xi we have to skip here as well. Xi minus xi plus 1, and up to which reach the nth coordinate xi minus xn. So this is very easy Lagrange interpolation polynomial. I hope this point was clear to you guys. Okay. So I already told you that. Let me write once again for you people. N is equal to total number of nodes in element. Total number of nodes in element. So if you people clear will be sharp enough to note that the numerator is actually a product of the terms of x minus x1, x minus x2 up to x minus xn. It is actually the product of this thing only. And the only term missing from the series is one associated with the ith node. Actually, xi, x minus xi is missing only from the numerator. And the denominator is the product of this xi minus x1, xi minus x2, and the only term missing from that is xi minus xi. That is actually equal to 0. So it is very important to know that. So there are some characteristics of this shape functions actually. So characteristics. Characteristics of shape functions. Okay. So what are the characteristics? First characteristic is that the value of shape function uh, at its own coordinate is equal to 1. Ni is equal to 1 at x is equal to xi. It's important. And one more important thing is it is 0 at other coordinate points. Ni is equal to 0 for all x equal to xj, where j is not equal to I. So I hope you are able to follow this terminology, because the characteristics of the ith shape function is considered associated with the node of the ith element. It's important to you note here. And actually, what is the second characteristics? Ni, when you will formulate the value of ni is a polynomial of order n minus 1. Okay, n is the number of nodes. So for example, we had two noded element. So here it was one node, this was two node, n equals 2. So you people remember shape functions, n1 was equal to x1 minus x divided by L. So if you people remember, what is the order of this shape function? Order is equal to order is equal to 1. So that is actually equal to n minus 1. That is equal to 2 minus 1 is equal to 1. So just recent few minutes ago we saw that for three noded element, 1, 2, 3. So n is equal to, sorry, n is equal to 3. So our shape function was something, n1 was something like this here. X minus n1 was x minus x2, x minus x3 divided by x1 minus x2, x1 minus x3. So if you will take the product, it will become a quadratic polynomial. So order here is actually equal to order here is equal to 2, which is actually equal to n minus 1, because n here is equal to 3. 3 minus 1 is equal to 2. So this is a quadratic polynomial. I hope this additional information, you got the additional information that I wanted to convey with you guys. Okay. So, and third characteristic, third characteristics that is important to note here is the nodes don't have to be evenly spaced. Okay. So this spacing, no, this is not important that they should be equally spaced. This will not affect the Lagrange interpolation function. Okay. No matter whatever will be the spacing of these nodes, this is independent. Lagrange interpolation function is independent of the spacing. Okay. So the nodes, do not have to be equally spaced. Okay, equally spaced. Okay, so we will do few examples and then we will see other things. Okay, let's take a few minutes break. So we are back. Actually, we will solve a few problems. Okay. So problem first for today's session. So problem first is we have to use Lagrange interpolation function to write down the trial solution for a two-noded linear element. So actually, we are having two-noded element in which the nodes are located at x1 is equal to 0 and x2 is actually equal to 2. And its nodal values are u1 is equal to 4 and u2 is equal to 1. We have to write the trial solution, that is we have to find uh, trial solution, that is u of x for it. What is u of x? We have to find u of x. So we know that u of x is actually equal to n1 u1 plus n2 u2. For that we will find first n1 then n2 and then multiply it with u1 and u2. Okay, so let us start. So if we will write the value of, we know that n1 is a shape function for, so first the number of nodes n is equal to 2. So the order of shape function is equal to n minus 1, that is equal to 2 minus 1 is equal to 1. So at least it will be of order 1. And one more thing, this trial solution will be also of order 1. Okay, so it will be n1 is actually equal to x minus x2 divided by length of the element, that is x1 minus x2. Okay, it is equal to what is x? X is nothing. X minus x2 is 1 divided by x1 minus x2, that is x1 is actually equal to, sorry, I'm writing wrong. x2 x2 is equal to 2 and x1 is equal to 0 minus x2 equal as 2. So it is 1 minus x by 2. Similarly, n2 will be equal to x minus x1 divided by x2 minus x1. Okay, so it will be actually x minus x1 is equal to 0 divided by x2 is equal to 2 minus 0. Okay, it will be x by 2. So finally our u of x will be equal to n1 u1 plus n2 u2. So n1 is equal to 1 minus x by 2. Hope you people are following. And the value of u1 is 4. It is given. Plus n2 is x by 2 and the value of u2 is 1. So when you solve this, u of x comes out to be 4 minus 3 by 2 x. Okay. So if you also plot the shape function, so n1 will be like this. This will be n1 and this will be n2. Okay, this will be n2. This is x equals 0, x equals 2. Okay, and the value of the shape function is, maximum value of the shape function is 1. Okay, I hope you people got this point. Then we will move to one more problem. So problem second. Okay, so same thing we have to do now for a three-noded element. So our element is like this. It is having one node here, one node here, one node here. So we are given the nodal coordinates x1 to be equal to 0, x2 to be equal to 2, and x3 to be equal to 6. So it's little bit spaced. Spacing is not equal, and the nodal degrees of degree value is u1 equal to 4, u2 equal to 3, and u3 equal -1 actually. So we have to actually write the trial solution for this. We have to write same. We have to write u of x. We have to write u of x for this. Okay, so we know that u of x for this, first we have to check what is the order. N is equal to 3, so order of trial solution will be, minimum order of the trial solution will be 3 minus 1, it is 2, that is quadratic. Okay, quadratic. And order of shear function as well will be same, quadratic. Okay, so it is the additional information that I am giving. Okay, additional. Okay, so u of x will be actually it will be n1, n2, n3 multiplied by u1, u2, u3. Okay, very simple. U1, u2, u3. You just don't get scared by this notation. It is simply n1 u1 plus n2 u2 plus n3 u3. It's just as simple as it is. Okay, then we can easily write the value of n1, n2, and n3 using Lagrange interpolation function very easily. So n1 will be equal to, easily n1 will be equal to x minus x2 x minus x3 divide by, so it's ith node, first node, so it will be x1 minus x2 x1 minus x3. So put the values of all the things. So x minus x2 is equal to 2, x minus x3 equals 6, divide by x1 is equal to 0, 0 minus x2 is 2, then 0 minus 6. So if you solve this, you will get 1 minus 2x by 3 plus x square by 12. Okay, this is one shear function. Similarly, n2 you have to write. Okay, n2 is equal to, so I is equal to now. So x minus x1 will be the above numerator. X minus x3 will be another one. Divide by x2 minus x1 times x2 minus x3. Okay. So the values are, so directly x minus x1 is 0, x minus x3 is 6, and x2 is itself equal 2 minus x1 is 0, it is 2 minus x3 is 6. So if you solve this, it will come out to be minus 1 by 12 of x plus 1 by 24 of x square. Okay, now directly I will be writing n3. So n3 is very simple. N3 is uh, x minus x2, because I is equal to 3 now, x minus x1, and denominator will contain x3 minus x1, x3 minus x2. Okay, so directly I will be putting the values, and I will get this to be equal to minus 1 by 12x plus 1 by 24 x square. Actually I wrote the wrong value for x2, so x2 will be equal to actually 3 by 4 of x minus x square by 8. Okay, so finally you will get the value of u of x. So u of x is equal to n1. What is the value of n1? N1 is 1 minus 2x by 3 plus x square by 12 times u1. What is value of n2? N2 is 3 by 4 of x minus, okay, x square by 8 of x u2. What is n3? N3 is minus x by 12 plus x square by 24 of u3. So the value of u1, u2, u3 you already know. u1 is equal to, what is u1 equal to? u1 is equal to 4, u2 is equal to 3, and u3 equal as -1. When you will substitute all these values, we will get u of x to be equal u of x to be equal to 4 minus x by 3. You have to perform the algebra there. X square by 12. Okay, very simple. Okay, so one thing we need to do is that if you note that all n1, n2, n3 are quadratic in nature, so their plot will look also quadratic in nature. So we will plot n1, n2, n3. Okay, so this is our coordinate axis. Let me take color violet for n1. So n1 will look something like this. Okay, let me take different color for n2. N2 will look something like this. Okay, yeah, and N3 will look something like this. Take a different color for that one as well. N3 will look something like this. Okay, so actually this is N3. So green color was N2 and violet color was N1, N1, and other values are with red color. This is actually this value is minus 0.2 and the topmost value for each one is 1 because the maximum value will be always 1. Maximum value, and this value is equal to, this is x equals 0 and x equals 6, and this point somewhere here, if this is x equals 2 something, it was like 2, x equals 2. So it's very take plot of shape function. Okay, I hope today's class was clear to you guys. Thank you everyone for joining this session. So if you guys have any questions, you can ask, otherwise you can leave. So in today's class, we saw higher order elements, what are their advantages and what were the disadvantages of the lower order elements, why we required higher order elements. I gave you the complete difference between higher or lower order and higher order elements. Then we saw the shape functions for second order problems, wherein we derived the shape functions for a three noded element, starting with a trial solution of quadratic order, that is second order. Then thereafter, I moved to a Lagrange interpolation function, wherein I showed you how to write the shape function for any ith node of an element with n number of nodes. Okay, then we solved two problems. So I think this is enough for today's class. We will be having one more class on Monday, that is 15. That will be the last class of this live session series. I hope all of you are enjoying this series and you are actually getting any benefit from my videos. All these videos are posted on the YouTube channel, and the links will be shared to you guys by the NPTEL team, as well as the PPTs. These PPTs are continuously updated on the Google Drive, and that Google Drive link is also shared with you guys. I hope you are enjoying it. Thank you, everyone, for joining these sessions and finding these sessions helpful. I got few mails from you guys wherein the feedback was very positive. Thank you very much. Actually, it motivates me. Your feedback motivates me for giving my best to the videos and explaining each and every concept very in a very simple manner, because the finite element course is a course which is little bit tricky or difficult, and especially it is in structural engineering, so it's little bit difficult. I hope you guys are getting any benefit from it, and all the best for your exams. Thank you everyone. You may leave.
Okay, thank you for the class.
Thank you.